Can a moon vanish? Surprisingly, the answer is yes, or at least it can appear to. In the early years of telescopic astronomy, the Saturnian moon Iapetus puzzled astronomers by pulling off a cosmic disappearing act. Some nights it was clearly visible, and then, without warning, it would vanish entirely. This baffling phenomenon left astronomers scratching their heads for centuries. But when they finally uncovered the reason, the mystery only deepened. Iapetus is a world of stark contrasts and enduring enigmas. One hemisphere of the moon is almost pitch black, while the other shines brightly like freshly fallen snow. To make things stranger, an immense mountain ridge wraps almost perfectly around its equator, forming a belt-like formation that defies easy explanation. What processes could have sculpted such an extraordinary feature on a world seemingly frozen in time? And what does Iapetus reveal about the early, chaotic days of our solar system? Let's go back to the beginning. The story starts in 1671 with the Italian-French astronomer Giovanni Domenico Cassini observing the night sky from the Paris Observatory. Using one of the most advanced refracting telescopes of his day, Cassini noticed a small, new point of light near Saturn. He had discovered a moon, later named Iapetus. But something was off. When Iapetus was on one side of Saturn, it was visible through his telescope. But as it moved to the opposite side of the planet, it would disappear, sometimes becoming so faint that even longer telescopes couldn't detect it. Cassini eventually realized that Iapetus must have one side significantly darker than the other. If the moon was tidally locked to Saturn, always showing the same face to the planet, just like our moon does to Earth, then its orbit meant that sometimes the dark side faced Earth, rendering it nearly invisible in 17th century instruments. This was a groundbreaking realization. For the first time, astronomers had detected surface features on a celestial body beyond the Earth-Moon system. Although Cassini named his discoveries after King Louis XIV, the naming convention didn't stick. Later, astronomer John Herschel proposed a more enduring system, naming Saturn's moons after titans from Greek mythology. Iapetus, the father of Atlas and Prometheus, was a fitting name for a moon of such dramatic duality. Despite its mysterious nature, Iapetus remained a tiny, enigmatic speck in the sky for centuries. Even the iconic Voyager missions of the late 1970s and early 1980s only provided distant glimpses. Voyager 1 confirmed the strange light-dark contrast, and Voyager 2 caught the first hints of an equatorial ridge. But detailed understanding would have to wait until a much closer look could be taken. That closer look arrived in 2004 with NASA's Cassini spacecraft. Appropriately named after Iapetus's discoverer, the Cassini mission spent over a decade studying Saturn and its moons in incredible detail. One of its most significant moments came in September 2007, when the spacecraft executed a close flyby of Iapetus, coming within 1,640 kilometers of its surface. The data it collected transformed Iapetus from a blurry enigma into a complex and fascinating world. Iapetus is Saturn's third largest moon, but it's relatively light, with a density just 1.2 times that of water. This indicates it's composed mostly of ice with some rock mixed in. The moon's surface is ancient and heavily cratered, showing few signs of geological activity. There's no evidence of a subsurface ocean or the tidal heating that powers internal activity on moons like Enceladus or Europa. Iapetus is cold, quiet, and seemingly inert. One of the first things scientists noted was Iapetus's unusual shape. Thanks to the equatorial ridge, it looks a bit like a walnut with a prominent bulge running around its middle. This feature is unique in the solar system and is still not fully understood. But we'll come back to that. Iapetus's orbit is also quite strange. It travels around Saturn at a distance of about 3.5 million kilometers, much farther than Saturn's other large moons. Its orbital path is inclined about 15 degrees relative to Saturn's equator, making it stand out among the generally flat, equatorial orbits of its sibling moons. This unusual orbit may hint at a turbulent formation history, perhaps involving migration or capture scenarios that pulled Iapetus into its current position. But it's the moon's surface that draws the most attention. Iapetus presents a striking two-tone appearance, with one hemisphere incredibly dark and the other dazzlingly bright. The leading hemisphere, the side that faces forward as Iapetus travels through space, is covered in a dark region called Cassini Regio. This area reflects only 3 to 5% of the sunlight that hits it, making it as dark as coal or asphalt. In contrast, the trailing hemisphere, including the regions called Roncevaux-Terra and Saragossa-Terra, has an albedo between 50 and 60%, comparable to fresh snow. The transition between these regions is sometimes gradual and sometimes incredibly sharp. Craters in the dark regions often expose bright, icy material underneath, and vice versa. Cassini images show this contrast in stunning detail, with the moon appearing as though it were split in two by an artist with a paintbrush. For a long time, scientists thought the dark material might come from inside the moon, perhaps from volcanic eruptions of a dark, tar-like substance. This theory was popularized in the 1980s based on data from Voyager, but Cassini's observations changed the story. High-resolution imaging and radar showed that the dark layer was thin, perhaps only a few decimeters thick. Beneath it, the moon is still bright ice. That meant the darkness must have come from outside. In 1982, scientists comparing the spectra of Iapetus's dark side found it resembled the composition of the Murchison meteorite, rich in carbon and organics. The most likely source of such material was Saturn's outer, irregular moon Phoebe. Unlike Iapetus, Phoebe orbits Saturn in the opposite direction and is much farther out. It's also dark and impacts on its surface eject particles that form a vast cloud of dust. This dust slowly spiraling inward towards Saturn due to solar radiation pressure through a process called the Poynting Roberts, and effect collides with Iapetus. Since Iapetus moves prograde and Phoebe's dust is retrograde, the leading hemisphere of Iapetus smashes directly into this incoming material. Like a car driving through a rainstorm, the front gets soaked while the back stays dry. This explains why the dark material primarily coats the leading side. Yet even this isn't the whole story. Scientists realized that once the dark dust landed, it kicked off a runaway feedback loop. The dark surface absorbed more sunlight, which slightly raised the temperature. That warmth, though minuscule by Earth standards, was enough to make the ice underneath start to sublimate, turning directly into vapor. Since Iapetus lacks an atmosphere, the sublimated water molecules launched away from the surface on ballistic paths. Where did the water go? It tended to recondense in the coldest areas, which were already icy and reflective. This made the bright regions brighter and the dark regions darker, a vicious cycle of thermal segregation. Over millions of years, this feedback sharpened the boundary between the hemispheres into the striking division we see today. It's an elegant explanation combining both external and internal processes. Dust from space sets the stage, and sunlight and sublimation do the rest. But Iapetus still had one more mystery in store: the equatorial ridge. Stretching more than 1,600 kilometers around the moon's equator, the ridge rises up to 20 kilometers high in places, dwarfing Earth's tallest mountains. From space, it looks like someone tried to zip Iapetus closed along its equator. This feature is visible almost exclusively within the dark Cassini Regio and appears ancient, heavily cratered, and geologically inactive. One popular theory suggests the ridge is a fossilized remnant of Iapetus's youthful spin. Early in its history, Iapetus may have rotated far more rapidly, perhaps once every 16 hours. Such rapid spinning would have created a bulge at the equator due to centrifugal force. If the moon cooled and solidified while spinning quickly, it would have retained that bulge even as gravitational interactions with Saturn slowed it down over millions of years. With the centrifugal support gone, the crust might have slumped, piling up along the equator and forming the ridge. Another possibility is that Iapetus once had its own ring system. If a small moon or debris ring orbited the moon early in its history, the material would naturally align along the equator. So, where does that leave us? The Cassini mission revealed Iapetus in unprecedented detail, confirming the source of its dark side, unraveling the thermal mechanisms behind its dramatic contrast, and capturing stunning images of its mountainous ridge. Yet, like any great magician's trick, the more we learn, the more questions arise. What exactly is the composition of the dark material? What caused the ridge to form with such symmetry and scale? Could future missions uncover even more secrets buried in Iapetus's ancient ice? For now, no follow-up mission is planned. Iapetus remains a distant, quiet world orbiting far from Saturn's bustling inner moons. But in that darkness lies the memory of a time when our solar system was young, chaotic, and full of wonders. Iapetus may no longer vanish from view, but its mysteries have not faded. In fact, they shine more brightly than ever, waiting for the next curious traveler to unlock their secrets. Eventually, tidal forces could have caused this ring to collapse and rain debris onto the surface, building up the ridge over time. This theory explains the ridge's location, but raises questions about how such a ring would have formed and remained stable long enough to collapse. Other theories suggest tectonic or convective forces could have pushed material upwards, but these lack clear evidence. A giant impact is also unlikely to produce such a narrow, continuous feature. The ridge remains one of the most perplexing geological structures in the solar system.